Hello, this is Naveen, your SAT Physics faculty. Today we are going to talk about simple harmonic motion. Simple harmonic motion is very interesting phenomena. Suppose I have a ball and I am throwing a ball like this. Is it simple harmonic motion or not? So basically, to understand simple harmonic motion, first of all we need to understand what oscillation is. I am throwing this ball from left hand to right hand. Okay, so this ball is repeating same path again and again. This falls under category of oscillations. Okay, but whenever oscillation takes place under influence of any restoring force, we call it simple harmonic motion. Okay, like you can see in this diagram where a spring is moving to and fro and this vibration is taking place after a certain time interval. So we can call it periodic motion or simple harmonic motion. Okay, so in this lecture we'll talk about some details about simple harmonic motion. Okay, let's move to the class. So let's take an example to understand simple harmonic motion in better way. Suppose there is a spring having a spring constant K and we attached a block of mass m at end of it, and this arrangement placed on a surface that is frictionless. Okay, so this initial state is a state of stable equilibrium. Now we are just trying to disturb the equilibrium of this system. So let's give a simple displacement to this object. Suppose we are stretching this object by a distance x and bringing it at position A. Now at this point, if we'll hold this object at this point, so the total work done by us will be stored in form of a potential energy at this point. And there will be a restoration force that will try to bring back this object at its original position. And the direction of this force will be directed towards center. We can find out the magnitude of force working on this object. That magnitude will be minus k into x. This is well-known Hooke's law, that restoration force applied by a spring on an object. Okay, so due to this force, this object will experience an acceleration. That acceleration is directed towards center. Okay, so we can find out acceleration on this object, that will be minus k over m into x. Now if we apply the fundamental concept of kinematics, so whenever there is an acceleration working on any object, so it will try to contribute in increment of the velocity. So when we release this object will start moving towards the center, and when the object will reach at this point, the object will have maximum velocity. So this potential energy will get converted in form of a kinetic energy due to maximum velocity. At this point, when spring will attain its natural length, there will be no spring force. So object will have maximum kinetic energy, but due to this velocity, this object will tend to move away from the center. Okay, so it will start compressing this spring. And due to compression of spring, the direction of force will be now in opposite direction of motion of the object. So object will experience a force, spring force minus k into x in this direction. Due to that, this object will become at rest after displacement of x from the center. And when object will become at rest, its velocity will become 0, hence total kinetic energy will again get converted in form of potential energy. So from this analysis we can say that the simple harmonic motion is all about exchange of energy. That potential energy changing in form of kinetic energy, then kinetic energy again changing in form of potential energy. Now we will assume that this surface is frictionless, then this object will continue this behavior for infinite amount of time. Now we can see the relationship between change of energy and position of this object. Here is a graph. You can see now from this graph we can understand that how energy exchange is taking place with the change of position of this object from extreme points to central point. And now at extreme point we can see that kinetic energy is minimum, and as object is moving towards the center, its velocity is increasing, and according to that the kinetic energy is increasing and it is getting maximum at central position. Now if object starts moving away from the center, then kinetic energy again starts decreasing and it is minimum at extreme point. On the other hand, at extreme point, when object is at rest, the potential energy is maximum and it is reducing as object is moving towards the center. And when kinetic energy is maximum at center, the potential energy is zero. And again, when object is moving away from the center, kinetic energy is reducing and potential energy is increasing. So the simple harmonic motion is a perfect example of conservation of energy, where kinetic energy changes in form of potential energy and potential energy changes in form of kinetic energy, but the overall energy of system remains constant. Now let's try to find out the expression for displacement of this object during simple harmonic motion. So let's plot a graph between displacement and time. Suppose on this axis we are taking displacement and on horizontal axis we are taking time. Now you can see this object is starting from rest. At this point displacement is 0. Now when we are stretching this object away from the center, then displacement is increasing. Suppose the maximum displacement of this object is A. So now when object will move towards the center, then this magnitude will start decreasing and it will again attain this position where amplitude is 0. Now object is moving backward in next condition, so this graph will go like this. It will again attain maximum amplitude in opposite direction A, then return back to central position. Now as we talked about, if surface is frictionless and this process will continue for infinite amount of time, then we can further draw this graph like this. Now it's a simple sinusoidal wave. Okay. Now if we'll consider the angular frequency of this object is omega. As we know, there is very simple relationship between angular frequency and general frequency, that is omega equals to 2 pi f or omega equals to 2 pi t. So we can take on this axis angular frequency into time, and it's a sine wave. So we can write simple expression for displacement, that is x equals to a sine omega t. Okay, in some books student will get an equation like this: a sine omega t plus phi, where phi is initial phase difference. But to maintain the simplicity of this discussion, we are taking this phi equals to 0. Let's take very ideal condition. So now we have expression for displacement x equals to a sine omega t. So let's use some basic fundamentals of kinematics, like velocity of any object is equals to rate of change of displacement. So let's differentiate this equation with respect to time. What we'll get? We'll get v equals to minus a omega cos omega t. So we got second relationship. Now we will further differentiate this equation for acceleration, that is a equals to dv over dt. We'll get a equals to minus a omega square sine omega t. Now we can plot all three parameters on this axis. We have already graph of displacement. If we'll draw velocity, so it's simple a cosine curve with negative magnitude. What we'll get? We'll get a graph like this. This is for velocity. Now we will try to plot amplitude acceleration. This is minus a omega square sine omega t. So it's a negative graph of sine. So we'll get a graph like this. Now from here we can find out very interesting fact for the relationship between displacement, velocity and acceleration. Let's mark 2 points. This is point of center. Let's take this is a point of maximum displacement. So at the central position you can see the graph of displacement having 0 value, the graph of acceleration having 0 value, but the velocity have maximum amplitude. On the other hand, at position of maximum displacement, your displacement is maximum, acceleration is maximum, but velocity is 0. Here acceleration is maximum, here displacement is maximum and velocity is 0. So we can make a simple chart for simple harmonic motion that if we'll draw 2 points like maximum displacement and center. So velocity is 0 at maximum displacement here and velocity is maximum at central position. Acceleration is 0 at central position and acceleration is maximum at maximum displacement. And from previous discussion we can write that potential energy is maximum at max displacement position and kinetic energy is 0 at max displacement position, and at central position potential energy will be 0 and kinetic energy will be maximum. So this is basic relationship between velocity, acceleration, displacement, potential energy and kinetic energy of an object during simple harmonic motion. Okay, so let's again return back to these basic equations what we derived for simple harmonic motion to find out some more interesting information. Now look at this equation. Equation for acceleration is a equals to minus a omega square sine omega t. So we can rewrite this equation as omega square a sine omega t. Now let's look at first equation. X equals to a sine omega t. So we can substitute in this equation value of this term and what we'll get? Omega square into x. And this is necessary condition for simple harmonic motion, that whenever any object will undergo simple harmonic motion, then displacement will be proportional to acceleration but in opposite direction. If any object satisfies this condition during motion, then motion will be simple harmonic motion. Okay, so here we have an expression for acceleration, that is a equals to minus omega square x. And in initial discussion we discussed that acceleration for any object under SHM will be minus k over m into x. So let's equate these two equations. What we'll get? That is minus omega square x is equals to minus k over m into x. So we'll get omega square is equals to k over m. And we can do some mathematics that will give us omega equals to k over m. Now during basic definition of simple harmonic motion, we talked about that any object, when any object moves to and fro and repeats same path after a certain time interval, that time interval is called time period of simple harmonic motion. So let's calculate time period of this object, that omega equals to 2 pi over t. So we can write t equals to 2 pi over omega, and from here we'll get the time period for SHM will be 2 pi under root m over k. So from here we can draw a conclusion that the time period of an object in spring arrangement will be dependent on mass of the object. So this is expression for time period of an object under simple harmonic motion. Okay. So in SAT examination, we basically face two kind of examples of simple harmonic motion. First one we already discussed, that is spring and mass arrangement. Second one is simple harmonic motion of a pendulum. Suppose there is a bob of mass m attached with a string of length L. So initially this arrangement is in position of stable equilibrium. Now we will try to disturb this balance by shifting this arrangement by an angle theta. So let's analyze the force working on this object. So due to gravity, this object will experience a gravitational mass that is m into g. So to understand the effect of this force, we can resolve this force in two directions. One is along this string and second one force directed towards the center. So this angle will be theta. We'll get first component, that is mg cos theta, and second component will be mg sin theta. So this force mg cos theta will be balanced by tension of this string, and this force mg sin theta will again try to restore the original position of this object. It means here is a restoring force. And if we'll calculate acceleration experienced by this object due to this force, this acceleration will be mg sin theta over m. It is g sin theta. And second important thing is, we are taking displacement in this direction and force is working in opposite direction. Then we can substitute a negative sign in front of it. So we have expression for acceleration, that is g sin theta. Now if we'll assume that this angular displacement is very small, then from the fundamental concept of trigonometry, we can say that is sin theta is equals to theta. Okay, and we can calculate theta for this arrangement from this concept. Like suppose the length of arc is x, angle is theta, and radius is L. So angle equals to arc over radius. So we can replace this sin theta by theta and then theta by x over L. So we'll have a new expression for acceleration, that is g over L into x. And now we can recall the fundamental condition for simple harmonic motion, that is acceleration must be proportional to displacement, that too in opposite direction. So this arrangement is satisfying this condition. It means this bob and string arrangement will undergo simple harmonic motion. Okay, so if we'll equate with the general expression of SHM, that is A equals to minus omega square x, what we'll get from these two equations. So now if we'll compare this equation, that is equation of bob, and general equation of simple harmonic motion, then we'll get omega square is equals to g over L. So omega is equals to under root g over L. So from this expression we can calculate time period of oscillation. Then time period of oscillation will be 2 pi over omega, that is 2 pi under root L over g. So from here we can conclude that the time period of a bob string arrangement or simple pendulum oscillation is dependent on length of the string and gravitational acceleration. So let's look at some examples of simple harmonic motion that is based on SAT physics examinations. So first question is, let's look at first question, that is which of the following exhibits simple harmonic motion. there are three different arrangements are given. First one is simple pendulum, second one is an ideal spring with a mass, and third one is a ball bouncing on a surface. Okay, so let's discuss one by one. In case of simple pendulum, when we give a simple displacement to an object, it experiences a force directed towards the center, that is due to the gravitational mass of this object, and this is mg sin theta if displacement is theta. So here we can see that the force is directed toward the center and the nature of this force is restoring. So the basic concept of simple harmonic motion is it's a type of oscillation which takes place under influence of any restoring force. So it means this pendulum will undergo simple harmonic motion. Let's take a look at second condition. Here is a spring, and a spring is attached with a mass m. So if we'll give a small displacement to this spring, so due to this stretch, it will experience a force by Hooke's law, that is minus k into x, that is directed towards center. So again this force is a restoring force, and here to and fro motion will take place under influence of a restoring force. So it's a simple harmonic motion. In third condition, there is a ball and ball is bouncing on a surface. It means it is moving up and down. So if we'll analyze the forces working on this ball, then we can see there will be a force that will act due to mass of this object, and the direction of this force will always directed towards the ground. It is not directed towards the center, whether ball is moving upward or ball is moving downward. So it is violating the basic fundamental of simple harmonic motion. So the ball bouncing back from the surface will not undergo in simple harmonic motion. Let's look at next question, that a block is attached to an ideal spring, undergoes simple harmonic motion. Its equilibrium position is x equals to 0 with an amplitude of a. What fraction of total energy in form of kinetic energy when displacement x is equals to a by 2? So let's analyze this question. In this question, there is an ideal spring. Suppose its spring constant is k. A block of mass m is attached with this spring, and the initial equilibrium position is x equals to 0. When this spring undergoes simple harmonic motion, then the maximum displacement is a. So now we can calculate potential energy of this object at maximum displacement. Potential energy can be expressed in terms of a spring constant, that is half k x square. At maximum displacement x equals to a, so we can find out maximum potential energy, that is half k square. Okay, so as we know, during simple harmonic motion, the potential energy changes its form in terms of kinetic energy, then kinetic energy changes in form of potential energy. So we can calculate potential energy at point where x equals to a by 2. So new potential energy at this point will be half k a by 2 whole square. So we'll get 1 by 8 k square. The concept of conservation of energy is mechanical energy equals to kinetic energy plus potential energy. When object has maximum displacement, then total mechanical energy is equals to potential energy. So we can write it as half k square. Now at position x equals to a by 2, the potential energy is 1 over 8 k square. Now we can calculate kinetic energy at this point. So we'll get 1 by 2 K square minus 1 by 8 K square, that is equals to kinetic energy. So we'll get kinetic energy of this object at x equals to a by 2 will be 3 by 4 into half Ka square. Simple mathematics that we can take out 1 by 2 Ka square outside, that is 1 minus 1 over 8. So this question is asking that what fraction of total energy in form of kinetic energy. So we can calculate fraction, that is kinetic energy divided by total energy. Total energy is half Ka square and kinetic energy is 3 by 4 into half Ka square. So this fraction will be 3 by 4 into half Ka square divided by half Ka square. So we'll get 3 by 4. It means the kinetic energy at x equals to a by 2 is 3 by 4th of total energy. Okay, let's look at next example, that a simple pendulum swings about vertical equilibrium position with maximum angular displacement of 5 degree and period of t. So initial displacement theta is 5 degree and time period is t. Okay, so if the same pendulum is given a maximum angular displacement of 10 degree, then what will be the new period? So next condition is when theta dash is equals to 10 degree, then what will be the new period? Okay. So let's look at the situation that what question is saying. There is a pendulum. It is initial equilibrium condition. First, we are giving angular displacement of 5 degree. Suppose length of this object is L, mass of this bob is m. So time period is t. In second case, we are increasing maximum displacement, that is of 10 degree. And we are interested to calculate new time period. So let's look at the formula for time period of a string bob situation, that is 2 pi under root L over G. So from this equation we can see that the time period of a pendulum is dependent on length of a string and gravitational acceleration. There is no dependence on angle of displacement, whether it is 5 degree or 10 degree. So the total time period of this pendulum will remain same, that is equals to t. So it's all about simple harmonic motion. Now you can attempt test series for further clarification of concept given here, and for further doubt removal session you can contact at this given link.